So next up, I'm happy to introduce a postdoc in the Amplab named Ameet Talwalkar and a grad student in the Amplab named Evan Sparks. They'll be talking about the new machine learning library project, or new machine learning project, of which the library is one component, named MLbase.
All right. Hi, everybody. Thanks for being here. So yeah, I'll be talking about MLbase. I'll be talking about MLbase. It's a distributed system for user-friendly machine learning. And this is joint work with Evan and myself, as well as many of our collaborators, in particular at the Amplab, but also at Brown and at VMware. So we're focusing on two different types of problems in this work. So the first is that scalable implementations of machine learning can be difficult for ML developers. And the idea here is that ML developers are, this isn't looking exactly right. Oh well, sorry. Well, the point is that a subset of ML developers, people like me, are more comfortable working in things like MATLAB, and we're stuck in what we call a MATLAB cage. The idea is that we're able to come up with fast prototypes in MATLAB, but then when it comes time to actually write scalable implementations, we fall short because we're using MATLAB. There are other open source distributed systems out there for machine learning. And they have their pros, but they're not very extensible, and they're pretty difficult to set up. On the other hand, machine learning can be very difficult for end users. So this is a picture of an end user that's stuck in what we call a machine learning maze. And the idea here is that someone who's not an expert in machine learning, it's often very challenging in that there's many algorithms to choose from, lots of knobs to tune for each of these algorithms, in the form of different parameters for these algorithms. Machine learning doesn't typically work right off the bat, and when things don't work, it's very difficult to debug what's actually going on. And finally, as I mentioned in the previous slide, scalability is an issue with existing implementations. Moreover, ML developers, machine learning research is an active field, but there's no real clear direction given by researchers and developers out there to guide end users in terms of how to use machine learning. So the idea with MLbase is that we want to come up with a system that brings together ML experts and systems experts to build this unified system that leads to, that provides a platform for easy-to-use development of machine learning, as well as user-friendly, execution of machine learning at scale. And along the way, we're gaining insight into data-intensive computing. In particular, we're pushing the envelope in Spark in certain directions and hopefully helping to make machine learning run faster on it. So in this talk, there's going to be 4 components. I'm first going to go over the overall vision of MLbase. Then Evan's going to take over and talk a little bit more about the details of this first component, or one of the components called the MLI, as well as talk about our current status. Then I'm going to come back again and talk a little bit about how our system fits in with a common machine learning workflow, and also give you some prep for the exercises you're going to be doing later today. Okay. So the animation is not working here. And I'm a little worried this is going to cause problems. Well, we'll see how it goes. But, so the idea is to give you an idea about how the overall stack looks, I'd like to make an analogy to MATLAB. So in MATLAB, you start with a single machine that's possibly multi-core. And the next level up is LAPACK, which is this low-level Fortran library that does a lot of the heavy lifting for numerical linear algebra. But the MATLAB that I'm at least comfortable with is the actual MATLAB interface. And it has higher level abstractions and a lot more functionality than just LAPACK, but whenever this heavy lifting needs to be done, inverting a matrix, multiplying large dense matrices, it leverages LAPACK whenever possible. And this isn't just a story for MATLAB, there's a similar story for R or Python and so on. All right, so with that in mind, MLbase looks as follows. So at the lowest level, we have the higher levels of MLbase we want to be agnostic to the runtime, but we need to start with some runtime, and Spark was, for many reasons, a very good choice. As everyone in this room at this point I'm sure knows, it's a cluster computing system designed for iterative computation. And on top of that, the lowest level of MLbase is what we call MLlib, and this is a low-level library written directly in Spark, released as part of the next release of Spark. and it's callable from both Scala and Java, and hopefully in the future from Python as well. Above that is MLI. MLlib is sort of an analogous to LAPACK. It's low-level functionality that's highly tuned and very fast. On top of that is the MLI, and this is more similar to the MATLAB interface. It has higher-level functionality, a wider range of functionality, and allows in particular for feature extraction, algorithm development, as well as evaluation of models. And again, the idea is that MLI and the next part on top of that are also both supposed to be platform independent. So the idea is that in the future, one day you can move to another system if you wanted to. And then the top level is what we call the ML optimizer. And the idea here is to automate the process of model selection. So for end users, again, the idea is that we want them in a declarative fashion to be able to specify their machine learning task, and then we want to solve a search problem over the space of all of the machine learning algorithms and feature extraction methods inside of the MLI and spit out an answer along with a summary of what we've done. Okay, so just to give you a concrete example of how these different pieces fit together or how you tackle the same problem using different components of a system, let's look at a very simple example. So imagine your goal is to classify a text document or text documents. Then this is how you go about doing that using MLlib. The idea is that you would first featureize the data yourself. So you take the raw text data and spit it out in a form that can be fed into a machine learning algorithm. You then call, so that's what's happening here with process data.
So I want to give you a couple examples of, kind of illustrating this point. So the first is, easy to use but not scalable. So in this case, this is actually a study that Ameet did with a collaborator here at Berkeley, working on this theoretical framework for, in this case, matrix factorization, but it's a meta-algorithm that applies to lots of different situations. It's a naturally distributed algorithm. They were writing a paper for NIPS, it was all theory, and they decided, hey, wouldn't it be nice if we built a prototype? So they built a prototype in MATLAB. The first version wasn't distributed. People actually wanted to use it, so they said, okay, let's make MATLAB distributed. So they got some MATLAB compiler out. They got an MPI cluster scheduler working. They built this distributed prototype involving compiled MATLAB, and it was just a lot of work to get this simple distributed algorithm working across a cluster. The second is scalable, but maybe not so easy to extend. So while we were doing an experiment evaluating the MLI earlier in the summer, we were looking at, wanting to do a head-to-head comparison against Mahout. And you'll see some of the results of that later in this talk. We wanted to make sure that we were really doing sort of an apples-to-apples comparison. And so in ALS, which is this matrix factorization algorithm, there's this thing you can do called early stopping. And I won't go into the details of what that is, but it should be about 3 lines of code to check whether some condition has happened, and then you can stop computation early. And we really thought this was going to be easy to figure out whether Mahout was doing it. But in practice, we had to go through about 7 files of source code, nearly 100,000 lines, just to check, or sorry, not 100,000, 1,000, just to check whether or not Mahout was doing this. And if it's that hard just to check whether something is happening in the code, I can't, it's tough to imagine really getting in and extending that easily. So we're introducing MLlib, which again is this core library of machine learning primitives in Spark, and MLI, which we hope to make things, leverage MLlib, but bring things up to that MATLAB or R level of sort of ease of use and interactivity. So to motivate this, I want to give you first an example of what the ML Developer API looks like. So when we first started building the system, it was natural to say, okay, Spark is pretty easy to use, it's great, it's fast, let's build just a machine learning system on top of Spark. So how do you want to represent your features? Well, obviously, they're just an array of numbers most of the time, so let's do that. And then you realize, okay, I want to do some basic matrix algebra, some dot products. Spark provides this vector library that we can use, that's great. And then you want to get some hardware support. So we say, okay, never mind, we're going to use this Breeze thing. And then you're like, oh, I want to use GPU-accelerated sparse matrices, so we link in this other backend. And it was all kind of a mess, and we realized we're trying to capture the same thing. We want to keep that backend abstracted away, so let's introduce one new object that can be all of these things behind it, called MLtable. MLtable is a relational table, supports map and reduce, and you can plug in arbitrary sort of data structures behind it to support it and make it fast. So again, it's this abstract idea. And also this gives us the benefit that it's a common interface that we can use against which we can implement all of our algorithms. And that helps us in this optimization task that Ameet talked about before, where we're searching over lots of different possible models. So the components of this system, the high-level goal of this system, rather, is to shield ML developers from low-level details. We don't want them to worry about, again, these crazy different backends for linear algebra. We want to provide them with familiar operations, mathematical operations, in a distributed setting. So the three components of this are first, again, I mentioned MLtable. We view this as sort of a general data container that has flexibility for loading data, so ETL, supports heterogeneous and missing data, so heterogeneous data across columns. Common interface for both feature extraction and data transformation, as well as the inputs to our machine learning algorithms. And it supports, again, map and reduce and relational operators. Second component is ML submatrix. And so one of the first questions is, why call it ML submatrix? Well, we want to make it clear that this is indeed a linear algebra library specifically for linear algebra operations on local partitions of your data. We're doing it this way because we want to discourage people from doing things like invert a billion by a billion matrix. That's not really computationally tractable no matter how you look at it, but a lot of these distributed machine learning algorithms can operate on local partitions of the data and then somehow coalesce results later. And so we get this fast linear algebra access to modern hardware by doing it this way, but while encouraging developers to keep things sort of computationally tractable. We may add support for distributed matrix algebra down the road, but that's not available in the first release. Importantly, we're also planning on both sparse and dense matrix support in the immediate future. So optimization primitives is the third component of this API, and so this is convex optimization. So things like stochastic gradient, parallel gradient, AdaGrad, LBFGS, these types of patterns that underlie many common modern machine learning algorithms. These primitives are used to solve these problems, build these models. And so sort of the punchline here is that, building on top of this API, building on top of these, three basic common objects, we're able to implement DFC, which is, in a fully distributed manner in about 50 lines of code. And this was the example I gave of Ameet, banging his head against the wall with MATLAB and cluster scheduling. And then ALS, we were able to implement early stopping in really, 3 lines of code, but more importantly, the whole algorithm fits into 40 lines of code. And I'll give you some more comparisons like that in a minute. So when we talk about ease of use of, a programming platform, one of the metrics that we use to evaluate this is lines of code. And so MATLAB is sort of the gold standard here for machine learning systems. You can do single node logistic regression in about 11 lines of code. You can do alternating least squares in 20. This isn't the only metric that you would want to think about ease of use, but we think it's a pretty good heuristic. So looking at the sort of the cutting edge modern distributed systems, we've got Vopal Wabbit, 700 lines of code. Similar story for alternating least squares in Mahout and GraphLab. And then under the MLI, though, we don't quite hit MATLAB level ease of use, but we're pretty close. And we're certainly an order of magnitude better in terms of lines of code compared to these other systems. Now, we're certainly getting some of this benefit from just running on top of Scala using Spark, but we think it's still a pretty compelling story. Now, looking at the other end of the spectrum, looking at scalability and performance, I want to talk about 3 ways that we evaluated these things. So first is just basic wall time. how long did it take to run a particular machine learning algorithm on a data set on top of MLI and Spark. So we evaluate this in two different ways. First is weak scaling, where we fix the problem size per processor. So that is, if the task is 10 gigs on one machine, as we add machines, we add another 10 gigs to the problem size. And you would like to see a nice flat line here in terms of as you add more machines, the task takes about the same amount of time. The other thing is strong scaling, where we keep the problem size fixed. As we add more machines, we'd like to see a linear decrease in the total amount of time it takes to train a model. So we ran all of our experiments on EC2, M2.4x large instances, up to 32 machines. So logistic regression, weak scaling, we see very competitive results with Vopel Wabbit. Again, a state-of-the-art cluster computing machine learning system. Neither system obviously hits the ideal case, but they both scale pretty well. The full data set here is about 200,000 images, 160,000 dense features, something like 250 gigabytes in size. And we also see very similar similar weak scaling to VW. So we're within about less than a factor of 2 of VW in terms of raw performance and wall time, and very similar sort of scaling characteristics. And of course, MATLAB, we're only running on one machine, but at some point the problem just gets too big for MATLAB. So the second piece is strong scaling. And this is, again, we want to see nice linear speed up here. We don't quite see that at all with VW, which is a little surprising. We see a better story with MLlib. We get better scaling in the strong scaling experiment, and actually we get to the point where we're faster than VW for this particular task as the cluster gets to 16 and 32 machines. And again, it's not really fair to compare MATLAB beyond one machine in this particular case. So then, looking at sort of a different flavor of algorithm, ALS for matrix completion, but again, an important thing that people care about, we see kind of a similar story. So MATLAB takes 16,000 seconds, Mahout 4,000, MLI and Spark, under 10 minutes, and similar story with GraphLab. GraphLab's a bit faster, but we're within spitting distance, I'd say, of their performance. So now I want to switch gears a little bit and talk about our current status. Right now in MLlib, this is sort of the core machine learning algorithm within Spark. We have the following features: linear regression, lasso and ridge, ALS, SVMs, k-means, kind of a representative family of some of the most widely used algorithms that are out there. And we have a parallel gradient optimization primitive. Within MLI, we either have implemented or plan to in the very short future or in active development, some additional algorithms, and importantly, additional optimization primitives, as well as feature extractors, and built mostly for text, but also PCA for dimensionality reduction, and some tools for model evaluation, so cross-val and other, in-sample, out-of-sample test error. So the current status of the stack, goal 1, our summer release, and I'm pleased to announce that just yesterday we made our developer release on GitHub. We made our repo open, so please go check it out. This involves both the MLlib, which many of you have seen, lives inside of Spark, as well as MLI, which we made public yesterday. And then second piece of our release is the optimizer that Ameet talked about before. This is sort of the high level. End user wants a classifier. They don't really care how it gets built. This is under active development now, and we're still shooting for a winter release for this. So future directions here. There's sort of a lot of open road in front of us in terms of what we can do in terms of building a machine learning library on top of Spark. So first is, we want to identify a minimal set of machine learning operators. So think of this as sort of what's the relational algebra for machine learning? What's the minimal set of things you need to be able to represent these algorithms? And then this could allow us to expose internals of these machine learning algorithms to sort of a more traditional database query optimizer. Certainly want to plug into other existing languages and frameworks, so it would be really nice to have really easy interop with Python or R. some more advanced visualization capabilities. So we think about this particularly in the context of unsupervised learning. So how do you tell the system that it's doing well building a model if you don't really know, what criteria that is a priori? And then second, of course, there's tons of different advanced machine learning capabilities that we could support. So time series graphical models, more advanced optimizations, online updates, et cetera, et cetera. The list goes on forever. But what we hope we've built is a good, solid platform for future development of distributed machine learning algorithms. And so with that, I'm going to switch over to Ameet, who's going to go into the details of the machine learning workflow and prep you for the exercise you're about to do.
Hi again. Yeah, so let's talk about typical machine learning workflow and how MLbase fits in with that, and then we'll talk a little bit more about the exercises. All right, so typical ML workflow or data analysis workflow. First, you have to obtain and load your data, and Spark is nice for that. It allows you to load data from a variety of sources. MLI also adds additional functionality, in particular for certain types of data formats that are common in machine learning, for instance, the libsvm format. Next, you do data exploration, and for now, we're relying on Spark, which, Spark Shell makes it, interactive exploration very nice. As Evan mentioned before, moving forward, we want to add visualization. We think that's really important into the MLI, but for now, that doesn't exist. Okay. Next, the next three things, feature extraction, learning, and evaluation, are components that are covered, or learning's covered in the MLlib. The other three are all covered in the MLI, and I'm going to go into more details about all three of these components in subsequent slides. And finally, there's deployment. So once you have a model, you've trained it, you've evaluated it, you're happy with it working, and you want to actually use it in the wild, how can you do that? And for now, you can call our trained algorithms, trained models within Scala. All right. So, oops. Yeah, so as I mentioned, I'd like to talk more about these three components and giving examples that you'll see in the exercises today. And this is going to all be in the context of binary classification. So starting very simple, what is binary classification? I'm sure you guys all know this, but the idea is that you have some entities and you want to learn mappings from these entities to discrete labels. In this case, two labels, yes, no, -1, 1. And there's lots of examples of binary classification. The canonical one is spam classification. So the idea is that your entities are emails, and the labels are spam or not spam. And the goal here is you're given a corpus of emails that have already been labeled as spam or not spam, and you want to have a model that is trained using this data, and then when given a new unlabeled data point, unlabeled email, can predict on the fly whether or not it's spam. All right, and of course there are many other examples: face detection, fraud detection, click-through prediction. And in the exercise, we are going to be relying on our favorite data set, the Wikipedia data set. And the idea is simply the wiki pages have labels. They're user-generated labels associated with them. We took two of these labels, arts and life, and we want to train a classifier to be able to predict, given a new document, whether it's arts or life. The key component here is that this is a real problem. This is not something that we made up. It's really, we downloaded Wikipedia data and we applied various components of the MLI to it. Okay, so with that in mind, let's talk about what a full classification pipeline entails. So you start with this full data set, and then the first thing you're going to do is randomly split into training and test sets, and I'll talk more about why that's so important later. But next, you're going to featureize your data. So basically, you're taking entities and coming up with actual features that you're then going to spit into a classifier for training. And finally, or next, you're going to, once you have this classifier, you're going to evaluate its performance on the test error to avoid overfitting. And then finally, once you're happy with this classifier, you can use it in the wild on new unseen data points. All right, so now let's talk about each of these components a little more. So first, the full data in the context of spam classification. This is an example of two data points in your full data set, one being spam, one not. That's pretty straightforward. The next thing you need to do is, so splitting it into training and tests is pretty straightforward. You just sample. Typically, the training set is bigger. The next thing you do is featureization. And the key idea here is that most classifiers, not all, but most, require numeric descriptions of your entities. So when you're starting with documents, you need to do something because you can't feed text directly into a classifier to train it. And so the idea, of course, is to transform your entity, whether or not it's originally numeric or in whatever form it's in. You want to represent it as a vector of real values. So again, when you're dealing with non-numeric data, this is required. But there are other advantages here, mainly that it allows you to incorporate domain-specific knowledge to the problem. And because of that, this is even something that's useful to do when your initial data is already numeric. Okay, so what are you guys going to be doing in your exercise today? Well, you're working with documents. So we're going to be working with bag of words representations of data. And again, this is pretty standard, but it's pretty powerful as well. So the idea here is that your entities are documents. So these are the two examples I showed you before. The documents, they're just text. The first thing you're going to do to create a bag of words representation is to build a vocabulary based on all of the words over your entire corpus of data. Once you do that, you want to derive a feature vector based on this vocabulary. In this case, it's very simple. The vocabulary consists of 8 words, and each of your documents is represented by the count of the number of times each of these words appear in your document. So that's kind of the simplest thing you can do. In the exercise, we're going to do something slightly more advanced. We're going to be using bigrams, which is basically the vocabulary is going to be the set of all adjacent words, so pairs of 2 in the full data set, and you're going to have counts of those or some weights associated with these bigrams. All right, so now you have training data. How do you actually perform classification? So again, this is a very, very well-studied problem. In these exercises, we're going to be working with support vector machines, and this is a one-slide summary of how support vector machines work. So the idea here is imagine you have you have data that's either red or blue. Those are your 2 classes, and you want to find a linear separator between them. So one thing you could do, there's an infinite number of linear separators between these 2 guys, and this is one, but your intuition would tell you that this is probably not the one you'd want to choose if you had your choice. You kind of want you want a separator that's further away from the 2 classes, something more like this picture on the right here. And that is, in some sense, the intuition behind SVMs. One way to think about them is that they are finding a linear separator that maximizes the margin or has the largest separation between the 2 classes. And this is a simplified example. This is assuming that the data is separable, meaning that some sort of linear separator exists, but that's not really interesting in practice because that never really happens. Also, it's enforcing a linear decision surface, which again you might not want, though in practice that often does work quite well. Turns out that SVMs can be extended very naturally to deal with both of these settings. So you can deal with a non-separable setting very easily, and also you can generate nonlinear classifiers using kernels, which I'm not going to talk about. Anyway, so that's the basic idea behind SVMs that you'll be using in the exercise today. We'll be looking, of course, at a non-separable setting because it's with real data, but we are going to be looking at linear kernel or linear decision surfaces. All right, and so finally, model evaluation. What are you doing? What are you doing here? How do you know that your model is actually good? Well, the whole point of having a test data set separate from the training set is that performance on if you give all of your data, your training data to a model and train on it, evaluating predictions based on that training data is overly optimistic, and that's not really what you want to do. You don't want to overfit to the training data. What you want to do is generalize. You want to have a model that generalizes to unseen data. And the idea here is that the test set simulates this performance on new entities or unseen data. So there's various metrics to estimate the quality of a new model. The most common one is just accuracy. So basically, are the 2 things, are the prediction and the ground truth label the same or not? Okay, and so how does this evaluation process go? This is, you'll see this in detail in the exercise, but just to give you a head start, the idea is simply you train on a training set, so you feed to the classifier the features as well as the label, but you tell them nothing about this training set. You don't expose the features or the labels of the test set. Once you've done the training, you now have this model. You now make predictions on the test set. You give to the classifier the features for the test set, and you compare them to the actual labels you have for the test set. That gives you some notion of accuracy by just computing the fraction of correct predictions. And this is the simplest thing you can do in practice. What people often do, or something more sophisticated like cross-validation. We're not going to do that today in our exercise, but that functionality does exist in the MLI. All right, so that's just a rough overview of what you'll be seeing today. And with that, I'd like to conclude and just note that, as Evan mentioned, our code is now all publicly available. It is an open source project. We really encourage contributions and feedback as to what is good and what is not good, what you'd like to see moving forward. And finally, I'd like to plug 2 things, none of which I'm directly associated with, but they're pretty neat, exciting around machine learning and big data. One is the Simons Institute in Berkeley have this series of, I guess, a fall series where there's a lot of visiting professors and scientists and a bunch of talks, and I'd highly encourage you guys to go check it out if you're around. Some really interesting stuff. And second, some people in the Amplab are organizing this Big Learn workshop at NIPS in December, which is very much at the intersection of machine learning and databases and large-scale computing, which should be pretty exciting. So, all right, thank you, and we'll take questions.
So yesterday, obviously, we spent a lot of time, not a lot of time, a little bit of time, learning about Spark streaming. And given MLbase's existence and goals, I wanted to ask about any plans to integrate Spark streaming with MLbase in support of conditional random fields, which seem like a really nice generalization of hidden Markov models that don't make the independence assumption that hidden Markov models do.
So, TD and I are planning on meeting sometime very soon. We're both very excited about extending. I agree completely that extending all of this stuff to the streaming setting is an obvious and natural thing to do. We haven't, we're planning on doing it, but more than that, I can't say much because it's in the works. But it's definitely on our radar and something that lots of people have asked about, and we want to explore in the near future. Back there, Andy.
Analogous question to the last one, integrating MLlib with Shark, the SQL aspect. Would you be able to call these machine learning algorithms from SQL directly?
Yeah, so I think the idea is that definitely the things inside of ML, the whole point of MLlib being within Spark is that some core functionality that is central to machine learning should be callable from various components that are leveraging Spark, including Shark. So in that sense, yes. Yeah, that.
I think hopefully it's a matter of writing a few UDFs that will call these algorithms directly. Just a second. Thank you.
So is Shark integrated part of your MLI? Is that what you're using as part of the table?
So no, actually the MLI, the current implementation.
Can you repeat that one?
Sorry, the question was, is Shark a component of the MLI today? Is that what we're using as our implementation for the table? The answer is no. Right now we're using a custom RDD format, but certainly a reasonable question and maybe something we might do in the future.
I'm wondering that the exercise today seems like it's pretty clearly geared for an ML end user, right? Is there any sort of walkthrough or anything for an ML developer if they wanted to try adding an algorithm, or not quite yet?
Not quite yet. If you look at the MLI code base, there's at least a couple examples of, the logistic regression code is probably a decent example of that, how you might go about that.
Yeah, I think, as Evan said, I think the point is that if you look at the MLI code, you see how some of these algorithms are implemented. It shouldn't be that difficult to just extend them. That's kind of the hope. Instead of looking through Mahout in 700 lines, if it's written in 40 lines, you can figure out how to tweak it or modify it as you want.
To extend on the previous question, do you guys have, I guess, a process for accepting outside contributors?
Sorry. Oh, there you are. Yeah, so I think that's something that is still underway. We're learning how to do that. The Spark guys have that mastered, and thankfully they're helping us navigate this a little bit. But yeah, so we've created these issues on the Jira site, the Spark's Jira site, with things that we're currently working on or would like to have added, but we're not currently working on. But if there's other things that you're interested in and want to contribute to, send us an email. I think the one thing that we've realized is that there thankfully is interest around this work. And we want to make sure that multiple people aren't working on the same thing at the same time. So we want to start announcing what we're doing so people can talk to us if they're interested or just not redo the work. Similarly, if you want to do something, we should create an issue about it. Other people know that you're working on it and that sort of thing. But yeah, the point of this is that we don't have a big enough team to write all of machine learning, obviously. And certain things are more important to the community. We want to crowdsource to see what people care about and have them help us build it.
And just want to add, during the final talk of the day, we're going to spend just a couple minutes walking through the general process for code contributions and ways that people can contribute to the projects all across the BDAS stack that you've seen in the last 2 days. So last question for this one.
So one of the biggest problems with machine learning in general is just having clean data. So the algorithms are sort of known. You don't really do anything different there, but are you doing anything for cleansing data before you actually run an algorithm?
Yeah, so I mean, that is the idea behind a lot of these feature extraction libraries that we've included inside MLI. In terms of, sort of raw, entity extraction, and, sometimes data is more messy than other times. So right now we've sort of offered some basic functionality. We'd certainly like to grow that over time.
Yeah, so do you want to shout out the names of those, Mike, or not yet?
Mike, hold on.
So what Mike said is that there are other projects that are in earlier stages in the Amplab that are focusing directly on data cleaning, and he will now tell you more.
Right. One, it goes by the name CrowdER, and it looks at using the crowdsourcing part of the Amplab agenda for doing entity resolution. And the other is what doesn't have a name yet, but I've been calling it sort of the love child of CrowdER and BlinkDB. And we're looking at where sampling and data cleaning fit in together. So.
That, by the way, is Mike Franklin, the director of the Amplab, who wasn't here yesterday, but is obviously a very important figure in the whole event.
So one more question, or do we have to wrap up?
Yeah, we can take one last one.
I think you mentioned it, but I was curious about filling in missing data. Do you see that as part of the featureization in the MLI, or do you see that as a collaboration with BlinkDB?
So dealing with missing data is definitely part of this. How you want, there's some algorithms that just allow you to have missing data, and they work okay. There's other algorithms that are going to impute that missing data.
Impute is what I meant, sorry.
There are also algorithms that, like matrix completion, the goal is to just do imputation. But the point is that, being able to read data and process it and make predictions on it with missing data is kind of necessary, because that will always be the case in practice. So.
All right, let's give Ameet and Evan another round of applause.